times 4 divided by well, that's one step too fast. For
Right.
the for the resistor 6 and the 12, I called it R equivalent, and it was equal to 4 times 12, 6 times 12 divided by 6 plus 12, which was 4. And then now Zx would be the 45 volts multiplied by the 4, and then divided by the 4 plus the 2, and that would be 30 volts.
Okay.
Right. Now, for after the switch is open, the circuit would no longer be in steady state, so the capacitor would start discharging. Right. So, and then I redrew this circuit, and I had the 12 and the 6 ohm resistor in parallel, and then in series with the 6 ohm resistor. So
6, 6, 12. Okay, so what's the equation?
So that would be, hold on, 6 times 12 over 6 plus 12, and then add it to 6.
So that's 6 plus 6 times 12 over 6 plus 12. Okay, that gives you 10.
Yes, sir. And then now, we, hold on, let me retrace. Right, so we want the current through that resistor, the 6 ohm.
Before we get to the current, so VC, what's VC?
Okay, VC would be V0, and V0 at this point would be the 30 that we just calculated.
Okay.
And multiplied by E to the, since it's discharging, E to the minus T over RC, which would now be the 10 and the 0.02 microfarad capacitor. Right. And all of that would be 30. Right. So I have 30 E to the minus T over 2 times 10 to the minus 6 over 0.2 times 10 to the minus 6. And then now we can calculate the total current in the circuit from that, because seeing that we have a resistor here.
But T, well, let's just get this. This would be 10 times 2 times, so that's 20. That's 0.05 over 10 to the 8. So that is 5t times 10 to the 6, right?
5t. Hold on. I don't have it like that.
Yes, sir.
So if you divide 30 by 10, divide 30 by 10, you get 3.
3.
And then, yes, sir.
All right. So that's VC. Yes. All right. So pause there. The other person's looking on. Do you have any difficulty with what Mr. Campbell has done so far? Everybody comfortable?
Sorry, Captain, probably can go back through it still.
No, we're not going back over it. I'm asking if you have any difficulty. Let's point specifically to the difficulty that you have. Because everyone was asked to do it. So did anybody not get what he has here?
Yes, sir. I didn't get it like that, but I understand why I got it wrong now.
Okay, all right, cool. That's the important thing. All right. So, Mr. Campbell, you said no. This. So we now have VC. What yes, do you want? We want I. Yes, and that's I. Okay. So, what's next?
All right. So the circuit is 6 and 12 in parallel, and then in series with the 6.
Okay.
So we can find the current in the.
Yeah, that.
We can find the. We just we just found the total current, which was 3 e to the minus t over 0.2 times 10 to the minus 6. So we can now use current divider rule to find the current to the 6 ohm resistor, which
That's all right. So IT, yes, on the circuit that we have here, that's IT.
yes,
IT, you said is equal to 3e to the minus 5t
5.
times 10 to the 6.
Yes, sir.
All right, okay. You're dividing this. You're dividing this current home.
All right, that's IT. Yes, we're dividing that current. So current divider. So it would be this value times the 12 ohm resistor, and then divided by 12 plus 6.
Okay.
And
So that gives us 2/3. So this should be IT. So this would give us 2 e to the minus 5t 10 to the 6.
Yes, sir.
Or I don't know why I'm writing it like this. All right, so that would be 5 times 10 to the 6t, right?
Yes, sir.
That looks better. All right, and that would be perfectly correct. Okay. So the idea is we're looking at what does it mean to be at steady state. And then, of course, we take it from there. Once we have removed the source, then we know that the capacitor will start discharging, more or less behaving like the source for the circuit. All right? All right. So we move from there. So we don't want to look at RL transients. We're maintaining the definitions. Most of what we set up, well, everything that we said about the definition of a transient, etc., all of that remains. All right. Yes. So for RL circuit, what we have here is an inductor in series with a resistor, and we want to look at the current and voltage responses. We're saying, as before, that here we have a current source. Yes. So it was originally, the current was passing through our inductor. And what do we know about the operation of inductors, generally speaking? What do you know about inductors? Anybody? In terms of the operation of an inductor, what can we say? What general statement can we make about the operation of an inductor?
Sir, opposite of the capacitor.
No, we won't use another element to define one. Speak specifically to the inductor. What do you know about an inductor, generally speaking, in terms of its operation? Just general statement.
Is it the inductor is purely resistive?
No, we can't say that. All right. Generally speaking, an inductor opposes change. All right. So, and you would have gotten that from Lenz's law. I'm sure we went through that when we were looking at RL circuits in AC. We spoke about that, right? So
Yes,
an
sir.
inductor opposes change. So with this inductor, when the switch was in position 1, what I can say to you is that initially, in position 1, the current through that inductor would have moved from 0 to I0. So it wouldn't immediately move, well, you wouldn't immediately see I0 through the inductor. All right, so it would move from 0 to I0 because initially the inductor would try to oppose the change. So if we apply a source to an inductor, the inductor would operate in such a manner that it would have an EMF equal and opposite to that change. And we get that from lens, right? But here, we're not, well, let me not say it that way. I withdraw that. So let's look at the energy that's contained in the electromagnetic field of our inductor. And we are showing that that energy is equal to half Li 0 squared. All right. So when I have that current passing through the inductor, with I0 through the inductor, the energy within the electromagnetic field is half Li 0. Okay. Now, this statement that we have here, I don't think I use it for the capacitor with respect to the voltage, and I'll speak to that later on anyway. But for your inductor, this is an extremely important statement, something that you need to pay keen attention to. All right, that I0 plus is equal to I0 minus is equal to I0. In other words, what this is saying is that the current flowing through the inductor just before closing the switch is the same current immediately after closing the switch. All right, so for the inductor, the current flowing just before the change is equal to the current immediately after the change. So if it was a situation where you had no current through the inductor, the same rule will apply. Meaning, if there's no current immediately before you make the switch or you make the change, then the current immediately after would also be equal to 0. In this instance, we have a current passing through the inductor. So after a time t, we would have had I0 passing through our inductor. And we are saying that immediately after closing the switch, that current, or removing the switch from 1 to 2, yes, that current will remain at I0. Please, students, keep that on the sticky side of your mind. All right, so having that in place, we now make the switch. So we are moving from position 1 to position 2. Right. Do we have the circuit?
Yes, sir.
Yes, sir.
Yes, sir.
All right, so from this, if we apply Kirchhoff's voltage law, so when I move the switch to this point, I know we'll have VL and VC in the circuit. So by Kirchhoff's
VR.
So by Kirchhoff's voltage law, I would now have VL plus VR. Okay, where VL is given by L di dt. So that's the inductance times the rate of change of current. And VR at any point in time would be equal to R times I. If I divide throughout by L, I get di dt plus R over Li equals 0. And of course, for this differential equation, it's homogeneous, as we know, yes? And because it's homogeneous, obviously it's saying to us that ultimately, as t tends towards infinity, then I is going to be equal to 0. In other words, our steady state value will be 0. So the current will ultimately go to 0. All right? Applying separation of variables, we have di over I is equal to minus r over L dt. Taking the integral of both sides, we have ln I is equal to minus RT over L. All right. We have ln I equal to minus RT over L plus K. And as we did with the capacitive circuit, we said that we'll have to determine the boundary conditions based on our circuit. And we know that at t equals 0, all right? So at the point that the switch was moved from point 1 to 2, position 1 to 2, yes? Remember the statement we made. Remember this statement here. Very important. Because that is true, it means that at t equals 0, yes, I is equal to I0. So it means that K is equal to ln I0. Right. So grouping, and we had done this something similar with the capacitor, which is why I'm not spending a lot of time going through this again. So simplifying, we get IT to be equal to I0 e to the minus RT over L. And just to show that what we have here makes sense, as we did with the capacitor, we want to determine what's the energy consumed by the resistor. Yes, to see if it is equal to the energy that was contained in the electromagnetic field of our inductor. So to do that, the instantaneous power delivered to the resistor, yes, will be I squared R. All right, so that's just squaring the, let me just go back up. So that's just squaring this. So we'll get that squared, and of course, that times 2, okay? So what we have there. And doing the integral from 0 to infinity for energy. Integral with respect to time, of course. And substituting right. So from 0 to infinity, we find that this would be equal to half Li 0 squared, which is equal to the energy in the inductor.
Sir, I can go over that part for me, sir. When I integrate from 0 to infinity, P of t dt.
All right, who is this, Mr. Wilson?
Yes, sir. Yes, sir.
All right, you were absent on Monday. We went through this in detail on Monday, so let's consult those notes for me, please.
Okay, sir.
Good. All right, so that's for our inductor. Now, if you recall, we had done, we had looked at the time constant for our RC circuit. So I'm just going to make brief reference to what we had done with the RC circuit. So for the RC, yes, this was the general form. Yeah. We're of course tau
I'm sorry, you could go back for just a second, sir. Okay, thanks, sir.
Yeah, no problem. Okay. So going back to our capacitive circuit, the general form that we had was Vc equal V0 e to the minus t over tau. Yes, where of course we had established that tau is a time constant. If we compare that to the current equation, yes, then we'd have IL being equal to I0 e to the minus t over tau, which implies, therefore, if we just compare the two circuits or two equations, yes, for the RL circuit, tau is equal to L over R. All right, so for your RC, we call that tau is equal to C times R, or yes. For your inductive circuit, we have L over R. All right, folks. And of course, as before, we'll give the graphical representation. Yes, the graphical representation. So for your inductor current, so it starts at I0, and as t tends towards infinity, the current through your inductor tends towards 0. And as before, in terms of definition, we spoke about if the current decreases at the same rate at any point. So if we were to find, oh Lord, if we were to draw a tangent, which I hope would look better than mine, right? So we're saying that at that point, the time taken, this time here, would be equal to tau, which drawn to scale, those two times would be equal. So if we take the tangent at any point, the time taken to fully discharge would be a time constant. Of course, the other classic definition is that it is the time taken to reach or to discharge through to by a factor of 1 over E, which would be your 36.8%. All right, so let me just take off. Okay. Any question? All right. Let me just run into a little problem there. Okay. This is not cooperating this afternoon. Any questions? It's quite similar to what we did on Monday. So let's just jump into some questions. So here we have 3 simple questions. In a series RL circuit, determine tau for R at 200K and L at 10 milli. This now can be treated like school's challenge. And then L for R equal 1K and tau 100 milliseconds. Everybody have this?
Just a second, sir. Okay, sir.
All right, so let me start with Mr. Clark. Marcel?
Yes, Chief.
You were absorbing on Monday, so come now.
I appreciate me not surprised that, but all right, me.
Can I have something like that? All right. R equal 200, L equal 10. I want tau. So that's tau equal to for the RL circuit.
All right. You said I equal 200.
No man. R equal 200, L equal 10. What's the formula for tau?
Could it equal L over R?
Yeah. That's all like question. L over R. What's L?
L is 10.
10 times 10 to the minus 3. 10 milli, huh?
Yes, sir.
And R?
And R is 200K.
200 times 10 to the 3.
All right, so plug that in. You're gonna get 5 times 10 to negative 8.
5 times 10 to the?
Negative 8. Yeah, to the negative 8. That's what I get.
Minus 8?
Yes, sir.
All right. But because we are in engineering, we don't talk like this, right? So it will be 50 nanoseconds, right?
Okay.
Alright? I will leave this to them science people. But
Sure, man.
engineer.
Right, you just write me telling you, sir, I don't know if you're right. I'm just do something based on, so I'm quite sure.
Then. It's not minor thing, Mr. Clark. All right. Yeah, it's fine. All right. So.
Take a whole heap out of me a while ago, so I'm not lying, but all right.
So if you know, man. Frighten you?
I will deal with her.
That's good, man. That's good. Miss Lynch? B. Miss Lynch?
Yes, sir.
B.
Okay, B would be, L would be tau by R.
Okay. So that's 100. 10 to the minus 3. Times R, which is 10 to the 3. I can't go no further and I come Miss Lynch. Miss Lynch. Miss Lynch, you still there?
Yes, sir. Yes, sir.
It's not calculator you're using.
Sir, hello?
Yeah, man, I'm waiting for the answer.
So 100 micro.
No, man, look carefully. You tell me you're multiplying, you know.
10 to the minus 3, 10 to the 3, cancel out to the 100.
Who is that grumbling in here?
No, sir, I was just saying 10 to the minus 3.
Nah, man, no. The last time he checked, Miss Lynch sounded like when remember the story of the wolf when the wolf eat shark. So Miss Lynch no sound so coarse. So come, Miss Lynch. Give me the answer.
So 1,000.
It's 100 times 10 to the minus 3 times 10 to the 3. All right. It's 100 henries, all right? All right. Who was coming in a while ago? Is it Mr. Adams?
Me, sir, what me do, sir?
Oh, I know you. All right. So who was coming in? All right, let me find somebody. Any volunteer?
Sir, I got 100 anyway, sir.
No, man, I'm dealing with C now, you know.
C. Okay.
Yeah, part C. Any volunteers? Oh, support your mic open. Go on. No? Yeah, man, accidents are good. Yeah, come, C. I'm listening. Where you get the 10 kilo from? What the question asked for? No, before you start plugging in numbers, right? Before you reach the numbers thing, what I want you to do is to look. No, before you say find R, look carefully at what the question says. What I ask you to do. What is halved? What is it that is halved? What's halved? The energy. Excellent. Now, for the energy to be halved, what is that? What's the implication? The halving. What's the formula for the energy stored in the inductor? Li squared. Well, Li squared. The I naught there just meant that we're looking at the initial energy. You with me? So the general formula would be half Li squared. So that being the case, if the energy is halved, what is that telling you?
So the inductance is off.
When I say the inductance can't change.
Sir, current
Huh?
to be half, sir. That's the-
Current would be a half. All right, so let's work with that. If the current is halved, forget about this now, what we're doing here. If I told you that, I'm sorry, I can't find an example that's simple. But anyway, let's think about power. Let's think about power. Yes? And we know power equal I squared R. Everybody agree with me?
Yes.
So if R remains constant and I reduce the current by a factor of a half, what would happen to the power?
So reduce by a quarter.
So it go down by a factor of a quarter. So how is it that the power would be halved? What factor must that be? Must the current be reduced by?
Root a half, sir.
All right, yeah. I had to think about that one to see how it look. All right? Yes, 1 over root 2.
Yes.
What if it? So it means that if you go to the expression I is equal to I0 e to the minus t to the minus t over tau. Okay? So it means therefore that I over I naught must be equal to 1 over root 2, and that's equal to e to the minus t over tau. Is there anyone who does not understand why it is 1 over root 2?
Me, sir.
I don't understand, sir.
You're not too sure. All right.
No.
E is equal to a half Li squared. You agree with that?
Yes.
Okay. So whatever the value of I is, whatever the value of L is, that's immaterial. However, what if I now reduce the current by a factor of 1 over root 2? I would have a half L, the same I, but I now have it over root 2 squared. What would that be equal to? Miss Donna?
I squared.
Miss Donna.
Half
Would that be?
L.
So you have a half L, 1 over root 2 all squared is what?
So that's a half.
And then we have the I squared. What's a half times a half?
1. No, a quarter, sorry. A quarter.
Yeah. So we have a quarter Li squared. Isn't this a half of that?
Oh, okay. Yes,
All right. Good.
sir.
So it means therefore that this current would have reached this factor of that.
Oh, okay, sir. I see.
Good. So from
Yes,
this,
sir.
you calculate R, because you have everything else. 10 would be T, yes, and 100 would be L. You rearrange that. Okay, so we'll move from that to the next question. Take this question for me quickly. Okay. Everybody have this? All right. Silence means consent. So let me see who. Oh, boy. Mr. Darby?
Yes, sir.
All right. So let's talk now firstly about the principles that you would apply to this circuit. Given what you have seen for the RC circuit, what principles do you think would apply here?
Sir, we can go to the formula. Hold on.
Before you go to the formula, let's deal with the principles. If you don't understand the principles, the formulas don't help. So what principles would you apply here?
Sir, I'm not really sure. I wasn't here until late in the Monday class.
So that you get out of jail. Excuse me, Mr. Darby.
No, sir. I'm trying to catch on.
All right, cool. I'll let you be. So Johnson, Antonio Johnson.
Yes, sir.
Okay, let's go through this. Principles. Let's tell me the principles you achieved on that.
Well, you know, so it says that it's steady state at t equals 0 minus. So you know that means that it's just before the switch opens.
Okay.
So you know that you'd have the full current flowing through the inductor.
All right. So the inductor, what would the inductor represent at this stage?
Would represent short circuit.
Absolutely. All right. Good. So it will be the reverse of the capacitor, right?
Yes, sir.
Okay. So you have a short circuit. Next.
And you can use the regular circuit analysis and find the current in the 50 ohm branch.
All right. And that current would give you what?
As in what is the value or what's the
No. What would it represent?
Current in the inductor just before opening the switch.
Which would represent what?
Steady state current.
When I open the switch, that current would represent what?
I0 minus.
Okay, so it would represent the, oh, you went on to minus, but it would represent the initial current. That's what I'm looking for. So the current at steady state would give you your I0. All right, carry on. So now I open the switch, and what happens?
When you open the switch, you know that it's still going to be I0, but it's going to start to decrease after that. I'm really too sure now, but
yeah, that's all right. Don't worry, nobody else is sure.
To be honest, sir, I would just apply. I would just try to find the current in that branch. Don't necessarily see the need to use any of the exponential formulas here.
Oh, but remember now, you know, that the fact that you have opened this circuit, yeah, the fact that you have opened the circuit by opening the switch, which is the only element in the circuit that would have some energy?
The inductor.
The inductor. So what do you think it's going to do?
Can lose energy after some time.
So if it's losing energy, it's gonna cause a current to flow, no?
Yes, sir.
So we'll have the fact that I'm opening the switch. What would I be creating? What is this whole topic about?
You're causing a change in current by doing that.
And this, which is called a
transient.
A transient. So therefore you must use, as you call it, the transient formula. All right. So let's go through this. So as he correctly said, at steady state, this would be like a short circuit. So it's act like a short circuit. So we'd need to find the current through the 50 ohm branch. And what would that current be equal to?
Like 100 over 50.
Exactly. So the current here would be 2 amperes. And note, it will be going downwards, yes?
Yes, sir.
Okay. When I so it means therefore, once I open the switch, the inductor will discharge through the set of resistors, yes? And the total resistance that the inductor would be experiencing or would see would be equal to what?
So it would be,
if a current is leaving the inductor, what's the resistance? What's the equivalent resistance?
you'd have 150 in parallel with 75, then in series with 50.
Who is this, Conrad?
Yes, sir.
All right. We do resistance equation around here. So it's 50 plus 150. You're not wrong, you know. But when things get a little more interesting.
Sure, and get 100 as a final result.
So that's 150 in parallel with 75 plus 50, and that gives you 100 ohms. So you now have Req. Okay. So it means therefore that E, or what am I saying? That I, instantaneous current for your inductor, would be I0. Because remember we said that I0 minus is equal to I0 plus. Yes. And in this case, it would be equal to 2 amperes. Yes. So it would be 2e to the minus t over tau, where tau is equal to L over R. L is 10 henries, and we just calculated R to be 100. Okay? So that's 0.1. So it means that I is equal to 2e to the minus 10 t. All right? So that's the expression for the current for the inductor. But what are we interested in finding?
Voltage across a 75 ohm resistor.
Okay, so if I know the current going here, what do I need to do?
Find a
the current divider.
Use current divider. All right. So if I use current divider, yes, we'll have V75, or sorry, I75 would be equal to IT times 150 or 225. Would you agree with that?
Yes, sir.
So it will be 2 times 150 over 225.
300 over 225. E to the 10t, negative 10t.
Yeah, and that sounds like $300 over 225.
4 over 3.
Huh?
4 over
4
3.
over 3. Okay. So it will be 4. I'm trying to find space on the. Everybody have everything that we have here? All right, I suppose that means yes. I can erase all of this up here. All right. All right, tell you what. I is equal to 4 over 3. So that's I through the 75 ohm is 4 over 3 e to the minus 10t. What if I? So it means that V is equal to 75 times I, which would give us 100 e to the minus 10t. Any dissenting voice? Any dissenting voice? Come on, somebody disagree, no? I was really hoping for some dissent, but that's not going to happen. Folks, look at the direction of flow of the current. Where's the current going?
Downwards.
So how would it be going through the 75?
Upwards.
Up. So you don't have a problem with what we have there.
Yes, sir.
What's the problem?
Negative.
Section with the enter is negative, sir. So
down here would have been plus, right?
Yes,
So that
sir.
means that the value is actually minus 100.
Yes.
Listen. Networks 1 wasn't just with one bench, you know. There's nothing that we did in Networks 1 that you will not apply in Networks 2 and for the rest of your engineering career. All right? Just remember that. We can't overlook those simple things. All right? Everybody good? We clear on this?
Yes, sir.
All right, cool.
Yes, sir.
All right, so take this one for me now. Okay. We have this.
1 second, sir. Yes, sir.
Okay. All right, so I'm going to allow you to chew on this one. If you have issues, then we'll address it later on. So we're going to move now to force response. All we have done so far, we have looked at circuits where the energy stored by the reactive elements, we use them to produce currents. All right, that's what we have done so far. So we have charged them, and then we apply them to circuits. That's what we have focused on. What we've been now looking at is where instead of just applying the reactive elements to the circuit, we want to look at circuits that have a voltage or a current source applied after time equals 0. Right, so that's the change. Whereas we would have just applied the storage elements, the reactive elements, to a resistive network. We're going to do the reverse now by applying a source after time t equals 0. Okay? And for that, that's where the whole issue of forced response comes in. So that's the change in this section. Now, for us to do the complete analysis, because I'm going to now apply a source. Remember, prior to this, we were sure that the elements would be fully discharged over time. Agreed? So whether it was the capacitor, we know that once the capacitor is fully charged, when we switch it across a resistor, ultimately the voltage across the capacitor is gonna be depleted and it's gonna go to zero. The same is true for the inductor. We have a current flowing through it, although the inductor opposes changes. We know that over time, the current through the inductor is gonna go to zero. Based on that fact, we know that our equations, the differential equations that we had, were all equal to zero, making them homogeneous, and therefore the particular solution zero. But now we are applying a source, so it means therefore that the result will obviously be non-zero values. So we now have non-homogeneous equations. Yes. So instead of just the complementary function, we'll have both complementary function and particular solution. And so that will give us the full solution to our networks. Now, I know I've said a mouthful, so let us just get into the maths of it and see where this takes us. So before we get into that, just take this note. Right? So the complete solution, which will now consist of both a transient, and it has a transient because I am making a change in the circuit. I'm opening a switch or I'm closing a switch. So I'll have that transient. But because I am now applying a source to the circuit, it means that the final value, final current or final voltage within the circuit will not be equal to zero. So it means that I will now also have a steady state value.
Go back to a steady state.
All right. So I have a value for steady state. Yes. Which means that I have a non-homogeneous differential equation. Yes. And we need the complete, for that complete solution, we need both transient and steady state. Or in other words, or to speak to that from a mathematical standpoint, we'll have to have the complementary function and the the particular solution. All right. Okay, so this is just my choice, but I find to explain these things, I find it easier to deal with the capacitor. So let me use a capacitor as reference. So here we go. So here's our circuit. I take that down and then we talk about it. All right. Now, for this circuit, we have a current source and a resistor. Yes. Switched across a capacitor with an initial voltage of V0. So let's make sure we understand this. Here's my current source. Here's my resistor. This is the parallel combination we're talking about. All right. This capacitor was already charged, and it was charged up to a voltage V0. So that's the scenario. All right. We're saying that being the case, once I have closed the switch, yes, once we have closed the switch, then we'll have these three branches all connected. And I can use nodal analysis. Don't get frightened. I know that nodal put people on edge. But all they are saying is that if I use nodal analysis, this current, once I close the switch, we'll have current going there, and we'll have current going there. That's all. All right, so I0, and we know nodal analysis is just the application of Kirchhoff's current law, right? So that being the case, we have I0 being equal to the current through the resistor, current through the capacitor. And I'm going to, okay. So this is IR. Let me just keep it in the same order, plus IR. That's IC plus IR. So C dV dt plus V over R, because remember now, the rate of change of voltage times the capacitance would give us a current through the capacitor. But at the same time, whatever voltage is across the capacitor would be equal to the voltage across the resistor, because they're in parallel, right? Or the other way around. They are in parallel because the voltage across them would be the same. Right? Okay, so we have that, applying nodal analysis. If you divide through by C, let's make things look a little, well, I'm not sure it make it look cleaner, but yeah. And our objective is that we want to head to separation of variables. So using separation of variables, and then we are going to integrate. So we have dt over RC, and we have dV over V minus RI0. Right? So that's minus dt over RC. Have I lost anybody? We all cool with this?
Yeah, look, sir.
You're looking. All right. So if I integrate, right, so you would have ln V minus Ri0 is equal to minus T over Rc plus K. Again, for networks, for power systems, unlike math, in order to find K, the boundary conditions, we have to look at what we have for, a circuit. So the circuit will inform us as to what, as to how to find K. But we're not going to rush to that just yet. All right? So this will give us V minus Ri0 e to the minus T over Rc plus K. Of course, since I'm adding the index, we can't really multiply it. So I can have e to the K. All right, so this would be e to the K times e to the minus T over Rc. All right? That's what this section is also equal to. And I'm doing that for my own convenience. So Since I'm multiplying, I'm going to call this e to the k a, right? Which is what we have here. So this is coming from this, right? And then I bring the ri 0 over. So I get v is equal to a e to the minus t over rc plus ri 0. All right. Brother, still with me?
Yes, sir.
Yes, so far.
So in other words, this is, well, I've said it before, but I'll just highlight it here. So the complete solution, yes, that is what we call the natural response. Okay? So this would, the complementary function, we know that would give us our transient. Yep. And then, of course, this is what we call the forced response. Yeah? And remember, the subheading that we're looking at is forced response. Yeah? And that's for my particular solution. So we have the transient, which comes from our complementary function, and the forced response. Yes? The forced response. So we can call this natural response. And over here, we have this as the forced response. Okay? And this is the complete solution for V. So V would have a transient and a steady state. Now, remember we said that in order to find our constants of integration, we have to look back at the circuit. Right? So if we look at our circuit to determine these values. This we know was true, that just before I close the switch, the voltage across the capacitor was V0. Just after closing the switch, it remains V0. So I said earlier that I hadn't given you this expression for the capacitor, but it is true. And for the inductor, I0 plus equal I0 minus would be equal to whatever I0 or the initial current would have been. Right? So at t equals 0, remember this is the equation that we are looking at. All right? This is the equation we are looking at. So at t equals 0, this is equal to 1. Yes? And we know that at t equals 0, this is equal to V0. All right? So that's where we get this. All right? So at t equals 0, V is equal to V0. At t equals 0, e to the 0 is 1. So we have A. That has no impact on R, I0. R doesn't change. I0 is the source that you applied. All right? So it means therefore that we rearrange this and we get A to be equal to V0 minus Ri0. So folks, the complete solution for this circuit would therefore be equal to Ri0 plus V0 minus Ri0 e to the minus t over Cr. So let us see if this formula makes sense. Before we go any further, let's see if this formula makes sense. Because we are saying that this is the solution to the circuit. Look back at your circuit for me. Let's look back at the circuit. And let's see, let me get some volunteers. Let me volunteer you. Ms. Barrett. Ms. Barrett?
Yes, sir.
Good. All right. So let's look at, you're looking at the circuit.
Yes, sir.
All right. And let's focus now on the equation here. Based on this equation, at t equals 0, what would this be equal to? At t equals 0, what is that equal to?
Sir, this will be equal to 0, sir. 1.
1.
Sorry.
1. E to the 0 is 1. All right. Now, if that is equal to 1, yes, what would Vt be equal to? So let's substitute that 1 for this part and tell me what Vt would be equal to. What would Vt? What would Vt be equal to?
RIO plus VO minus RIO.
Which is equal to?
VO, sir.
VO. So in other words, at the point I close the switch, because remember what we are interested in is the voltage across the capacitor, right? So at the point I close the switch, which is t equals 0, the voltage on the capacitor remains V0. And we know that that is true. So we're good, no? All right, so since Miss Barrett is on a roll, I will continue with her. Yes, Miss Barrett. As t tends towards infinity, what is that equal to? Towards infinity, what does that tend towards?
It will be the natural response.
No, man, hold on. As t, just work with me. This part that I circle here, as t tends towards infinity, what does this little section equal?
0, sir.
0.
Yes, sir.
So as t tends towards infinity, what is Vt? Just look at the formula.
As it tends towards 0, what does t equal to, sir?
No, man. As t tends towards infinity, this section goes to 0, right?
Yes, sir.
If that goes to 0, what does Vt? What is Vt?
Vt will be equal to VO.
No, man. Look at the equation, man. I don't want you to guess. Just look at what is on the screen. If this is 0, what is all of this equal to?
0, sir.
0, man. So what is V? Vt?
RIO.
Ri0. All right? No,
Yes.
the reason I ask you all to keep an eye on the circuit. Let's go back to the circuit. At t equals 0, we just showed that VC would be equal to V0. Everybody agree with that? And we have it there. So we prove that. As t tends towards infinity, no, t tends towards infinity means that what? What's the implication? If the switch is closed for a long time, as t tends towards infinity, what does that mean?
Means the capacitor would have fully discharged, sir.
It can't be fully discharged. It's fully charged. So we're reaching a steady state. That's the implication. That's what you mean? Oh, yeah, son. Be careful, man. All right. So it means that you would have reached steady state. Yes? If I'm at steady state, what is the new current through the capacitor?
0, sir.
Huh?
0, sir. There would be no current through the capacitor.
0,
sir.
because it's now at steady state. So if the current through the capacitor is 0, what is the current through the resistor?
I0.
I0. So if I0 is passing through the resistor, what's the voltage across it?
PO.
If I0, R times I0, which is what we just showed with this, because at infinity, this tends towards 0, which means that VT tends towards RI0, because all the current will now be flowing through
Resistor.
the resistor. All right? So it's not just about getting some formula and trying to understand some formula. It has to make sense. It has to make electrical sense. All right? So we can show this graphically. All right? So the forced response is that the voltage across the capacitor, the initial voltage was V0, yes, but it moves to RI0. The natural response, that's for the transient portion. Remember this would now be the transient. So this part is the transient, yeah? And this is the forced response. So this is the natural, and this is VF. So this is your time axis as t tends towards infinity. V tends towards RI0. So the forced response tends towards RI0. And the transient response, or the natural response, that would tend towards 0. So the transient dies out. And that is what happens in your electrical circuit. When you make a change, you're going to have this transient. But over time, the transient disappears and you reach steady state. So whether you're dealing with power, it's not such a good example, but I'll use it anyway. Sometimes when you have a power outage, when they restore the electricity, if you didn't turn off your lights, you just see a light flicker a little, and then it comes back on. I'm assuming that you have had that experience. All right? That little flicker is as a result of a transient. So you have that little flicker. And then, steady state, you get full power. In fourth year, I'll tell you why. But for now, you just take it. That it is true.
I'd say.
All right. So what this represents is really a new steady state. So it takes us from the original steady state where the capacitor was initially charged, yes, and then it takes it to a new steady state. And that, students, is the basis on which we are going to do the analysis for forced response. All right? If we want to find the current, we know current is equal to C dV dt. So that's the current through the capacitor. Remember now that the two were in parallel. So the resistor and the capacitor are in parallel. So if we want the current through the resistor, we just subtract it from I0. So if we do that, then IR is I0 minus IC. Yes, which means that IR is equal to I0 plus V minus RI0 over R. So I have introduced this to you in a manner that is, maybe I will call it atypical, meaning normally I would just hit you with statements rather than, use an example to explain. So from this RC circuit, we are going to make some general points and conclusions on this forced response thing. And then we take 2 questions. It's 6:30, so we should be able to take a couple questions and hopefully solidify. The theory. Okay, so here are the general statements. In general, the complete solution for a forced response for a time-independent source is of the form. So that's the general expression. All right. And then from this general expression, we are going to define A and B. So B is a steady state solution. So in other words, when I apply that second source, I'm going to find the steady state, the final steady state or the new steady state for my circuit. So just for the example I gave you, the B would have been found by using the source, which is the I0, because that source would create a new steady state for me. Right? And as we said, it is as the function tends towards infinity. And tau and A, we find those from the function f of t equal to f of t minus b. So whatever b is, we're going to subtract it from the original function. That one may not be very clear. So when we go through an example or through the example, you will hopefully appreciate what we're saying here. All right. So let's go through 2 quick examples. And then we, just to test to see whether or not they understand what is happening. Everybody have this?
Yes, sir.
Okay. So there is a question. State that for me. And in the meantime, I will do the register. Across there is for Brown. Some Brown absent. Absent. So far, stand up with us today, all right? So grab that down. Great. Lewis. All right, go back to, oh yeah, okay. So, first thing we would need to do, remember what we're after is this general expression. This is what we're after, all right? And once we have that general expression, where in order to get it, we want to find B, we want to find A, and tau. All right? So we want to find A, B, and tau. That's our objective. All right. So with the switch in position 1, note what it says. It said the question tells you that it is in position 1 for a long time. What does that mean? What does that imply? Anybody? What does that imply?
T turn to infinity.
So the inductor is now,
Go again?
so the inductor is now short circuit.
Okay, which means that we have a steady state situation, yes?
Yes, sir.
Yes, sir.
Good. So in position 1, we know that the current is 1.25. So before I make the switch to position 2, which is why we're saying before the switch, just before I0 minus, it's 1.25 amperes. Yes? And we know based on what we had before, that I0 minus is equal to I0 plus. So when I switch it from point 1 to point 2, the initial current would still be 1.25. Everybody clear with that? So I0 minus equal I0 plus. So the current flowing through the inductor, current flowing through this, 1.25 at 0 plus, so at the point of closing the switch. All right, now, long after I close the switch, so when I move the switch from 1 to 2, so I now have the switch closed. So this is now out of the circuit, yes? Long after I have closed the switch, what can you say?
Current through the
Go ahead, man, inductor.
It said that 1.25 amperes that's caused by the inductor, so it will be 0 now.
It can't be 0. I've now switched it to a 10-volt source.
Yes, sir, but I'm saying that 1.5 that is a result of the inductor, sir. It would be 0 now, but you would still have the current from the 10-volt source.
No, we can't say it will be 0. Remember, you know. No, this was the reason I emphasized having moved the switch to point 2, and I said after a long while. First of all, the fact that I have switched from 1 to 2, what would I have created?
Closed circuit
or caused. What would I have caused by making a switch?
Transient, sir.
A transient. So I have created a transient. And after the transient, what going to happen? After the transient has passed,
Steady state.
I get the steady state. So, and the steady state is what happens after a long while.
Long term. Okay.
Exactly. So I'm now saying, when I move it to position 2 after a long while, what can you say about the current through the circuit?
It would be the 10 volts divided by 40 ohms.
40 ohms.
Okay, so it's 10 over 40, which is
0.425 amperes.
0.25. What is it? 0.25. Now, go back to the definitions that we just gave you. Yes? What did you say D was equal to?
Steady state, sir. Steady state solution.
The new steady state. All right? So long after the switch is moved to 2, I at infinity is 10 over 40, which you just said, which is 0.25. And based on the definition that we gave earlier, this would be equal to B. All right? So D is the current at infinity, which is 0.25 ampere. Now, the definition I also gave you for A, what did we say A was equal to? We said it was the function, yes, minus B. All right? Or f of t, the initial, whatever the initial was, minus B. So A is equal to I0 plus minus B. And I0 plus was 1.25. So that was the initial current. So we don't have A. Remember what we're trying to find? What are the things we're trying to find? A
and B,
and
tau.
And tau. Those are the three things we're finding. So we have found A, we have found B, we just now need tau. And tau is usually the easiest one. So tau is L over R. And if you had a combination of resistors that it would go through, then that would be you'll find R equivalent. Okay?
Yes, sir.
So it's L over R. So we have 0.5 times 10 to the minus 3. So the complete solution, this is A, this is B, and this is 1 over tau. And that's it. So that's with an inductor. Let me do the other one with a capacitor. And don't worry, I don't expect you to grasp it all this evening. And there are a number of questions in Schoology to which you have access. So you can go there, try them. You have the solutions there. Knock yourself out when you're not clear about, and we'll try and address that. So here's another one. Okay. Here again, we have a circuit in position 1, and then we're switching it to position 2. First thing it's not clearly stated here, but let's assume that it's in position 1 for a long time, which means therefore that the capacitor would be at
Fully charged.
Right? Fully charged. Now, if a capacitor is fully charged, what will be the voltage across it?
100 volts. No.
100, yeah, man. Do not change. Do not change it. Right?
So, but you have a resistor, sir.
It doesn't matter.
Okay.
Remember, what happens, the resistor is only dictating the rate at which the capacitor gets charged.
Okay.
But ultimately, it will be fully charged by whatever voltage is connected to it. All right?
Yes.
Yes, Mr. Campbell.
Okay, so I noticed that you just said we can assume. We assume that it is in steady state. It has been on for a long time. So it is therefore safe then from now on that if you don't get the instruction, just assume say it is on for a long time.
No.
Okay.
If you don't get the instruction, make a reasonable assumption.
Okay. All right.
I'm not going to tell you what to assume.
All right, sir.
Good. All right. So it will charge 200 volts. By continuity of charge, we know VC0 minus equals 0 plus. And once we switch it to position 2, yes, once we switch it to position 2, going back to the circuit, when I switch to position 2, after a long while, what will be the voltage across the capacitor?
50 volts.
All right. Can I have someone challenging that?
Minus 50, sir.
Minus 50.
Yeah, minus 50.
Listen, we never do networks one for nothing. All right, so it's minus 50. All right. Don't make them make things through you. So what is B?
B is equal to 150.
No, sir. How did we define B? B is the new steady state value.
Yeah, B is negative 50, sir.
So it's minus 50. All right. And how did we define A?
Initial conditions minus B.
Okay. So it means that initial is 100. Yes. B is minus 50. Therefore, A is 150. Okay. So the expression, and of course, RC. So the expression is VC. This is your transient. This is your final steady state. Again, ladies and gentlemen, we need to look back at the circuit. The circuit you drew as t tends towards infinity. Yes, as t tends towards infinity, this would tend towards 0. Agreed? Which means that VC in position 2 would be equal to 50 volts, minus 50 volts. When t is equal to 0, that's just before you switch. When t is equal to 0, this section here would be equal to 1. So you have 150 minus 50, you get 100, which is what we set up here. All right? So just look back at the circuit and you will agree that all of that is true. What we were asked to find was the voltage across the resistor. So since we have the switch at position 2, we know that VC plus VR plus 50 equals 0. Because a closed loop, applying KVL. Yes? So if you go around that loop, that's the equation that you would have. So it means that VR is equal to minus 150 e to the minus 250. All right. That is it for single transients. So we have looked at source-free circuits. We have looked at force response. To wrap it up, we look at double energy. So our circuit so far has just included either a resistor or a capacitor. We could have looked at two mesh circuits. It's not on your syllabus, but so we're not going to spend time going through that. However, we look at double energy transients, meaning you have an inductor and a capacitor in your circuit. And we'll see how that works out. Just let me give some final, just remind you of what we'll obtain on Friday afternoon. I know it's already there in your module outline, but for clarity, I'll go it over again today. The test that you'll get will be a 2-hour test. It will cover everything up to 2-port networks. You'll have short answer and or multiple choice. Although you'll be selecting or putting in those values, for it to be validated, for it to be marked, you must, I repeat, you must also upload the solutions. So the inclusion of the use of the multiple choice or short answer is just to provide you with feedback in the shortest possible time. I, however, need the written solution. Do not put in a solution for a problem that you have not worked. All right? And we are putting in these systems, students, because of some of what transpired at the end of semester 2. I will not go into that, but some of us may know what had transpired. So remember, although it's multiple choice, you must present the work solution. You're gonna upload that, and that will be uploaded 15 minutes after the end of the test. Do I make myself clear? Any questions?
Yes, sir.
I didn't know how long the test will be, sir.
Was.
So, sir, there will be a link on Schoology where we should upload.
Yes, it will be there.
Okay, sir.
All right.
Question, sir.
Yes.
So what if when you're working out you made a mistake and you send the workout sheet, but the answer was wrong on the Schoology?
The exam will allow you to make changes. So there should be no discrepancy between what you have written in on Schoology and what is on your paper. There should be absolutely no difference.
No, sir. I was wondering if we made a mistake in the calculations and you didn't pick up the mistake after submitting. If you would check the workout.
No, but what I'm saying, what you would put into Schoology is what's on the paper. So there should be no discrepancy. Because you won't be working the paper after you finish the exam, you know. You're working the exam on the paper. You're doing it on your sheets, on your folder sheets. When you get the answer, you put it into Schoology. That's it. So there should be absolutely no discrepancy. And you won't have time after the exam to check results. What you're doing, you're submitting the document that you have used to supply the answers. So there be no difference between the two, or ought to be no difference between the two. All right?
Okay, sir.
All right. Have a good evening. Take care.
Sir, question. So,
Uh-huh.
Sir, in the case that you were working a question, but the answer you got is not that exact answer that you have, and we just put the closest possible answer and we indicate on the paper that we estimated it to be that value that you have.
Most of the responses will be done to 4 DPs. So I encourage you to work with 5. So you should really have no, there should be no dissonance between the actual values and what you have calculated.
All right, thanks, sir.
All right, then all the best. Rest before you do the exam, please.
Sir, what time of day will the exam be administered?
Please check your schedule. I don't recall what it is offhand, but it is in Schoology. It has been there since June 1. All that information is there. All right?
Okay, sir.
Good.